Hello everyone, my name is Tamara Molyarova and I'm going to tell you about this work which is done by a group of authors and is devoted to modeling dynamics of volatiles in protoplanetary disks with dust evolution. Apart from dust grains and gas, protoplanetary disks also contain ices. These ices are thought to affect dust properties and even cause observable changes in dust distributions and emission. Laboratory studies show that the presence of ice mantles and dust grains can make them less fragile and, in fact, increase their fragmentation velocity. We wanted to consider this effect using a 2D hydrodynamic model called FEOSAD, which considers the evolution of protoplanetary disks since the very collapse of the cloud and also includes dust evolution. So we take this model and include their evolution of volatiles. There are two populations of dust in this model, small submicron dust that moves along with the gas, and also a larger dust grains, which we call grown dust, that have a variable upper size and moves relatively to gas. The dust growth model is such that the slope of dust size distribution remains the same and the discontinuity between the two dust populations smooths out after the step of dust growth. The evolution of volatiles is described by the surface densities of them in the gas phase, on the surface of small dust, and on the surface of grown dust grains. The evolution is described by this system of equations, which describes the accretion of gas onto two dust populations, the thermal desorption, photodesorption by interstellar UV radiation, and also the exchange of ice mantles between two dust populations. We can calculate the thickness of ice mantles on dust grains, especially on grown dust grains. And if the thickness of mantles is less than one layer, we consider that these dust grains are bare silicates and have lower fragmentation velocity of 1.5 meters per second. And if there is more than one monolayer of ice on grown dust, then we think that these grains are icy and have high fragmentation velocity. We consider four volatiles in our model, the major ones: water, carbon dioxide, CO, and methane. Their relative abundances are based on observational data for protostellar cores, and we also consider two values of alpha parameter. Let us first look at the distribution of various disk parameters in the model with alpha equal 10 to minus 2. Here we see free time moments and we see the values of gas surface density, dust surface density, grown dust and small dust, dust to gas ratio, and maximum dust size. You see that at early time steps, the disk is highly gravitationally unstable. It has very prominent spirals and clumps, and then it becomes more stable, it spreads out, and at 500,000 years, yes, we have a disk which is nearly perfectly axially symmetric. There are some spirals in the gas, but in the dust we have rather rings. Grown dust dominates over small dust, except for the very inner parts of the disk. We can see that with time, total amount of dust decreases as the dust drifts inside and falls to the star. And also in this model, we can see that dust size grows towards the center of the disk, but in the very inner disk, there is a cavity where dust size is 2 orders of magnitude lower, and it can serve at all time steps. If we compare that to the same picture for 10 to minus 4 alpha model, we see that it is nearly the same, except for the disk is a little bit smaller, and it is not that gravitationally unstable because of a lower alpha parameter. And we can see that in dust size, there is no cavity in the inner disk. This is one of the main differences between the models. Let us now look in more detail at the evolution of disk parameters in the model with alpha equal 10 to minus 2. Here are the space-time diagrams. They show azimutally averaged values of gas surface density, dust surface density grown in small one, dust to gas ratio, and maximum dust size, changing with the time along the horizontal axis. Also, we have this figure that shows maximum dust size divided by the maximum dust size allowed by fragmentation. And this figure demonstrates in which regions of the disk dust size is determined by fragmentation. So these are the orange ones outlined by black contours. As we can see, in the inner disk, in a significant part of the disk in this model, the dust size is determined by fragmentation, and only in the outer part, it is not so. Only in the outer parts, the dust size is governed by radial drift. That's why we can see the impact of dust fragmentation on dust parameters. As we see here, inside this blue line, dust size is 2 orders of magnitude lower, and also there is a higher surface density of small dust and higher amount of dust in total. This blue line shows the position of thermal snow line of water. So inside this line, dust grains are bare and they have no ice mantles. That's why they become more fragile. That lowers the fragmentation size, frag, and that decreases the size of the dust. That's why we also have increased amount of small dust grains, and they do not drift to the center relative to gas. So we have a high amount of dust in general. If we look at the distribution of volatiles at the same diagrams in the gas phase, on the surface of ground dust grains and on the surface of small dust grains, we can see that there are multiple snow lines for each of the molecules. Apart from the main thermal snow line, which we have seen in the previous slide, there is also another snow line, inverted one, in the envelope in the outer disk. This snow line is produced by photodesorption, and also in the outer parts of the disk, photodissociation of gas phase molecules will be efficient. That would destroy also those molecules. So we cannot be sure that these molecules are present in the gas phase, but we also know that there are no ices in the envelope due to photodissoption. If we look closely at the distribution of ices on small grains in this, for example, in these plots, we will see that near the snow lines, there is more ices on small dust. They accumulate by the snow lines, and in CH4 and CO, we can also see that ices on ground dust are elevated, and in the gas phase, there are the bumps by the snow lines. So ices, volatiles accumulate by the thermal snow lines in all their phases. If we look at the distribution of volatiles, we can see that the shape of the snow lines is very complex. It is not just a circle. It is shaped by the presence of spirals, which are warmer and denser. And the spirals also move through the gas, move through the disk, causing the evaporation of volatiles. And then when the spiral is gone, the volatiles settle back to dust surface. And as the total surface area of small grains here is larger than the total surface area of ground dust grains, the volatiles settle mainly to the surface of small dust grains. That's why we see that the relative amount of ices on small dust grains is large here. It even exceeds the amount of the dust contained in small dust itself. And this causes this pattern of ice distribution around the spirals. If we look at the average radial distribution of ices relative to gas, we can see that it changes not only along the disk, the composition of ice mantles changes with time. At first, all the ice mantles are mainly made of water and CO2, but then as the disk cools down and the dust particles drift inwards, we see that there is more CO, and in the outer parts of the disk, there are mantles of small grains that are made exclusively of CO. And we can see that most ices are on the ground dust at later stages. Let's go back to the model with 10⁻⁴. Here we see that the water snow line does not cause such a prominent change in dust properties. The dust size doesn't drop, the amount of small dust doesn't go higher. That's because in this disk model, the dust size is not determined by fragmentation most of the disk, but it is rather governed by radial drift. That's why we do not see sharp changes caused by fragmentation properties. But in this model, there is a prominent system of dark dust rings in the inner disk, and they are created in the dead zone, and these dust rings also cause changes in the distribution of ices. For example, if we look at the ices on small dust, we can see that, for example, for CO2, there are multiple snow lines because of these complex dust structures occurring in the inner disk. And we can see that the accumulation of volatiles on small dust is even more strong in this model. There are much more ices on small grains. Spirals are less noticeable here, but they also lead to the accumulation of ices. And in this model, there is so much ice on small dust that ice mantles are hundreds of times more massive than the dust grains themselves. These are these regions where there are some spikes in ice distributions. They reach 0.5 up there at the highest. So we see that there are small dust grains that are covered by one molecule and with the thick mantles of one molecule, which can be different molecule, water, CO2, CO, or CH4. So these conclusions sum up pretty much all I wanted to say. Thank you very much for your attention, and goodbye.